Let us go ahead and get ourselves started tonight. It's kind of a light night tonight. Is that a reflection of a midterm week and everything that's due with next? Yeah, sort of stuff like that. Plus, we can always kind of watch it online. So yeah, that's always your safety net when you have other things that you need to get going with. Okay. Today we're hopefully going to cover some pretty fun stuff that I like an awful lot. We're going to be looking at kind of finishing up the structural side of things, at least in terms of the basic framing mechanisms, and kind of look at how that whole notion of calculating things and being able to optimize the size of things using the analysis tools kind of play into helping you update your Revit models, your building models, so that you can take advantage of all that. We're also going to kind of start diving down the whole path of really mechanical systems in a building. So within that, starting to look at probably the simplest and most fundamental mechanical systems that we have in a building. That's what is handling ventilation. So it's moving air through the space. It's kind of taking care of our fresh air needs, so we're all healthy and comfortable in the building. We're not going to worry about the whole issue of heating or chilling that air. Just kind of moving the air through the space. And it's kind of a good space to start, and then we can get into like all the different strategies for conditioning that air to kind of either chill it or kind of make it warmer as we need. Okay, as we get going today, there's a couple of places you might want to get started. You can download the Section 12 starting point file in Revit. That's the file that's pretty much where we left off last time. The loads are applied to it, all that kind of good stuff. The boundary conditions are applied to it. So I'm going to take that into the robot structural application and just show you how you can go through and use that to do the beam size optimization, the column size optimization, just based on kind of code design calculations. So that application, Robot Structural, not on all these machines right now, but if you'll watch along for a little bit, you can definitely go ahead and load that on your own machines if you want to. We're just going to do the kind of basic calculations for the clouds here, because it uses the same engine, whether it's going through the cloud or whether it's going through the application. The advantage of going through the application is, though, that takes it one step further in terms of being able to use the auto sizing and go through and change things, whereas the cloud's pretty much one way. It's kind of giving you the information in terms of what the calculations present. The application actually gives you the ability to start changing things relative to that. So to get going, what I'm going to do is just go ahead and open up, and you can if you want to too. It's just what's called the Session 12 starting point. So let me see if I can go out there and find it for us. So if I go on out and 120B, let's just open that guy up and take a look. Because this should look fairly familiar, because this is where we left off last time. It really is sort of a very basic multi-base structure that has some columns in here, has some boundary conditions in there, has some loads on it. And I believe the way we left it last time is we actually put some braces in there too. So let's just going to confirm that they are there. There they are on the back side. Here's what's going on. So it's supported on two sides pretty well by braces. We might actually want to go ahead and add some more braces, or we can analyze it this way. Yeah. And from this, we can go ahead and just start thinking with the calculations and ultimately how to sort of size something like this. So our intent is, that ultimately you can take a small piece of your building and do something similar in terms of sizing things up. So if you want to use the automated tools, super. If you just want to kind of use the calculator to figure out whether your beams are appropriately sized or overloaded, or whether there's some room to go ahead and make them a little smaller, that's okay too. You don't have to go ahead and use the automated procedure. It works really well for steel frame construction. It's a little rougher for other types. It also is pretty good with reinforced concrete construction. But don't feel like you have to use that tool. Really, whatever mechanism you know of. If you aren't very familiar with structural analysis and going ahead and doing design work, and the TAs and I can kind of help steer you in the right direction of how you can take some portion of your building and figure out some of the sizes. So again, don't think that you have to sort of size up the entire building. A lot of the structures that we're looking at here are pretty complicated. There's a lot of stuff going in there, and it would actually be quite a task to go through and do a complete structural design. We just want you to sort of get the sense that out of the Revit model, out of the BIM model, you can go ahead and use those elements and the sizes there as the basis for calculation, and then use it to actually record your results so that the architects and everyone else can kind of use your results in their work. So I'm going to start with this guy, which is, again, loaded up with some live loads, a little bit of dead load here. And in order to get going with analysis, what I did was I went to the Analyze tab, and I found some tools over here for robot structural analysis, either analyzing in the cloud or sending it over to the desktop application.
And again, how I actually got that, just in case you don't have it, and you probably don't have it on your machine, looks something like this. Let me go ahead and say that, what is it, appexchange.autodesk.com. That's the place we tend to go when we are looking for things that extend Revit. You can go to the Revit Tools, and within here, they have a bunch of tools that are all about structural design. So these are connectors for a lot of different things. Looks like export to eTabs is there. So if you want to take your things over to eTabs, you go ahead and download this. It's a little 3D extension, and it'll take it over to eTabs for you. There's a CSI one, no, CIS, as opposed to CSI. That won't be as good. But really what I'm going to do is use a structural analysis toolkit there. That's the one that ultimately takes it towards robot structural. So if you want to go ahead and download it, you can. And it's just free, and it'll install. And just put those extra extensions in there. What are they doing? They're really just helping you take the Revit model, pull the information out, and take it over to the analysis tool. So kind of a common thread to a lot of the analysis applications now is that you can almost start thinking about Revit as a modeling platform that gets extended in a bunch of ways. There's extensions to do energy, extensions to do structural, there can be extensions to look at water, structures to look at, just all sorts of other functionality to it. So it's kind of a platform at the core of a lot of things. Some plumbing design extensions. I haven't looked over that recently. We should look over there later. Some things to actually help us. Interesting. Add hangers in. It's all sorts of interesting stuff out here. Okay, but enough of all that. Let's go back over and show you what it looks like when it's in place. So we're over here. We got this tab in the Analyze section, which includes robot structural analysis. And what I did to export them was just chose robot structural analysis link. And what that does is just decomposes our model, takes away the excess information, and really just strips it down to the core of the analysis model. So the single line representation and the connections between all the different elements, as well as the loads and the boundary conditions. And why are we doing this? It's really just to save you the trouble of having to go through and redefine it in eTabs or redefine it over in Robot Structural. So I'll just say, let's go ahead and take a look. I'll go back over to Robot, and that's what it looks like. Okay, so at a really simple level, yeah, it should look pretty similar to what we started out with over in Revit. Now, in this application, again, you can look at, turn on different things or turn off different things. It's a little bit different than Revit, but let me kind of show you where you can find some different things. There's a display under the View menu, which lets you control what you want to look at. And if you choose that, we can turn on and off all sorts of different things. For example, for the bars, all the different elements there, if you want to show the section names, you can turn that on, and I'll apply that. And that will show me just all the sizes that I put into Revit. So I can see I have some W10 by 40 something or others, 12 by 26s. Looks like almost everything is 12 by 26s. So let's start out with a very kind of common size that we're going to now go through and change and do a little more optimization on. You know, all these bars also have names. You should know about that, just because that's how they actually get referred to in this program. There is, you know, column 1, column 2, column 8, beam 1, or these are 20 is where they start all the way up to 46. You know, there's all these different sort of names that ultimately will then, we'll need to know them. Ultimately, that's how we sort of refer to things. And what we can do is, let me go ahead and just say OK to this, is actually turn on, there's a little bit of a browser view, or an inspector. See if we can bring that up. It actually shows you there's a little hierarchy over here. There's 32 different beams. There's 49 nodes that describe this. There's 9 columns that describe it, and they all have names. Okay, and that'll come in useful in just a little bit, because it'll snap, you know, we need to sort of refer to them and let the program know what we're talking about. For each of these different guys over here, you can go through and look at its properties. So if I click on, for example, beam 13, I'll see that what is going on with it right now. It's a 12 by 26 made of steel, ASTM, and a grade there. So a lot of information that ultimately came out of the model. You can also see it highlighted over here. So as a starting point, super. Okay, it's looking okay. We can get going. The loads are here too. They didn't get lost in the way. So let's go ahead and take a look at where they are. If I say View and Display, Let me go ahead and just turn off the bar descriptions because that's going to get very cluttered over there in a little bit. I'll say, let's go ahead and take a look at, I can put the load symbols and the load values if I want in there. Okay, so it looks like I have just one of the loads in there. That's interesting, looks like I only have the live load in there. Okay. What I can do now is, in addition to kind of just showing the loads, I can go through and say, let's just do a preliminary analysis on this to really understand, what the deflections would look like, what the shear bending moment would look like based on the load that's in there right now. So it looks like it's the dead load. Something at the minus 100 right now. So I believe that's what we sort of assigned as the dead load to this. Dead load, live load. Ah, they actually are both in there. It's showing me different loads for different cases. I can sort of change the load. But what we can do is say, let's go through and calculate some results based on this. And what I usually do is, I do this thing where I say, let me go ahead and show diagrams on the bars. Okay, we need to run some calculations. They haven't been run yet. So it'll go through and do a little bit of calcing. And then based on that, it's showing us all sorts of information here. But what I tend to like to do is, if I want to show the bending moment diagrams, I could turn that on. I can start to look at the bending moments on all of the different beams. Let's go ahead and see if we can actually figure out how else to show this. In terms of how we show this, we can do things like just showing things, there's on one particular beam, kind of the bending moment diagram there. If we want to, we can go through and put labels on it at the extremes. So that'll kind of show you what the high and low values are at those different locations. You can also decide, whether you want it to be filled or just whatever it is that graphically appeals to you in terms of showing those different things. So you can start to see where the higher values are, where the lower values are, which is a little bit useful. Let me go back and put no labels on there again. I can see as I just look at this structure right now, I got a couple things that are sort of interesting. These beams are definitely carrying more load than the ones going in this direction. That makes sense in terms of how they're spanning. This center beam, you can see it so well there because the grid is kind of cluttering it up a little bit. Let's see if I can rotate that around a little bit for you. Yeah. It actually has a bigger bending moment on that. That sort of makes sense because what's happening here is loads coming from both sides to that center line of beams. These ones on the edges, aren't nearly as badly loaded. It's kind of interesting. What's happening over here, there's definitely something funky going on over here. There's not so much shear and bending moment on those, and it has to do with those braces being there. Somehow that brace is actually shortening the spanning length quite a bit, so much less over here than it's actually happening over there. You can also see that there's a huge load really on that center column, and it sort of makes sense. There's a lot of heavy load coming from two sides. It's all kind of happening right there. So we can look at it that way in terms of just looking at the shear and bending moment diagrams. The other thing you can do that's really useful is you can choose any beam or any element, and maybe do it this way. I'll take it in the browser. I can go ahead and highlight any beam, or if I'll do it over here. I want to see if there's beam the 16. If I right-click on it, I can say, let's take a look at its properties. And then we start seeing a little more kind of detail about the whole thing. So in terms of the shear and bending moment diagrams, hang on, I'm looking in the wrong way. In the Z direction, going from positive to negative. And there's what the bending moment looks like on it. And we can just kind of see in some detail really what's happening there and decide how we want to look at things. You can also say that really at a high level we would like to do some code check on it. And I can tell that right now, just based on a set of criteria, this is not going to be a great section. There's something about it that's not quite right relative to the strength of the materials. And I can see real highly that it has this efficiency ratio, that overall notion of how well it's doing. It's 5.6. I know it's loaded a lot worse than it can be. Something's going to fail about this beam. Whether it's going to displace too much, or we're going to have some sort of a bending moment failure. More than likely, I'm betting it's going to be a displacement thing. But we can get to all the detail of sort of figuring that out. In fact, if we want to look at the displacements, what's happening there? It looks like in the center of that beam, it's dropping around 2 inches right now. And it's probably not considered acceptable in terms of what's going on. So we need to go through and fix those things. So here's how you start to think about fixing these things. So I got my basic analysis going here. It's not looking too bad. When I want to go through and start doing some design, what I do is I actually shift on over and let me go ahead and go to, well, before we even get there, let me kind of take a look at sort of the loads and the load combinations and make sure we have them all defined properly. I can define my own manual combinations, but I can also use the automatic combinations, and that's usually a good way to do it, kind of based on sort of the different code that you're using to design. Oh, I usually turn on simplified automatic calculation combinations, and it'll generate all those loading cases that you have to generate for that. So all the little combinations, let me say OK to that. I can even say more to that. And you can start seeing the different rules and combinations that it applies to something like that. So I can say super. Go ahead and create those combinations so that as it's doing the analysis, it will make sure to consider all those different combinations for us. So now even up in here, simple cases will be all those simple cases, really, whichever one's going to be the dominant one versus a specific load. Okay, so we start with doing that. Then we say, let's go ahead and do some design, and I can show you how that works. And we'll do it by going over to the Design tab. And if we're doing steel design, let's take a look at that. So I got my little structure over here. I've got basically, two different windows over here. One window is going to let us go through and choose specific members to take a look at. And this other window is going to let us go through and decide really what we want to verify and figure out, are we just kind of verifying it relative to the code? Are we going to go through and do some design and optimization relative to the code? Have some choices in here. But it all starts up here with just choosing the members and going from there. So what I showed last time, and one of the easiest things to do is something that looks like this. I will go through and say, I would like to, for the bars, okay, not just go ahead and just verify a single member. In this case, it's suggesting bar 16 because that's what I had selected when I went into the satellite. If I want to actually go through and verify a whole collection of bars, I can say, let's take a look at the list. And if I say any and put them all up there, it just basically changes it to 1 to 45. So every member is going to be considered right now. Okay? And in a big building, you may not want to do that. If you have hundreds of stories, that could be quite a list. Often we sort of subdivide and conquer and look at a specific issue at a time. So that's not so bad. We'll just go ahead and say that's looking pretty good. Okay, in terms of what we're going to do now, if we just want to do a calculation, what we can do is do a calculation. We can say how we want to consider the limit state to be, whether it's ultimate or serviceability. And when I do say calculations, okay, some things do not apply. I'll leave it that way. 42 to 45, those are those braces. I know they're the last ones we added. And I can see that, relative to those criteria, some things are looking good, some things aren't looking so good. So we have all these columns that are looking pretty good. We have a column over here that isn't. And always when I look at this notion of the ratio, that's kind of an overall metric of really what it is. And they're all being calculated for code case, design load, or dead load 1. Let's kind of roll on down there. It's dead load, it's sort of the dominant case right now. If we go down to the beams, you can also see that these beams, there's some that are having some pretty severe problems in here, kind of towards the center. We need to kind of do some adjusting to all these things. So a couple ways you can do that. You can go through and start adjusting the beams time and again, one at a time, analyze them, and for any of these different beams, really try and figure out what the story is with the beam. So for this one, we can see a little about its internal forces, what the strength is. We can try to figure out what the issue is and try to correct that. Okay. But let me kind of show you another way that's kind of interesting too. So it starts with this whole notion of just finding out where the problems are, changing those elements, and then going through and ultimately doing the calculations again. But let's talk about another way we can approach this. It's actually pretty good. Let me go ahead and cancel it. I don't want to save that right now. I think I'm going to turn off save calculation results. Not so important to me. Eventually it'd be important to you. Okay, so here's what we're going to do. We would actually like to go through and do a little optimization where we actually have it help us figure out really what the right sizes are. It's actually pretty smart about doing that. And in order to do that, here's what we got to do. Now, you could say, let's just go ahead and figure out the right sizes of every member at the same time. But that's kind of a complicated thing for it to do because there's a lot of members serving different functions, and if we chose the one right size of steel that would be perfect for every member, okay, you'd probably get something that really wouldn't be very meaningful in the long run. So what we're going to do is actually sort of subdivide and conquer the problem a little bit by taking that structure and doing two things. We're going to think about the different elements of the structure and kind of putting them into different categories that belong together. So for example, the columns might all go together. I could say that the exterior columns are different from the interior columns. Okay, that might be useful categories. When I start thinking about the beams, the exterior edge beams are probably different than these two beams in here, the interior beams, because they're double loaded versus those only being single loaded. So I might put those four together and those two together. And all these front to back beams, they're actually pretty similar in the scheme of things. They don't really change a whole lot given the way this is designed. And braces, again, are its own separate thing. So here's how you go through and do that. And it works the same. We're just going to sort of do something for a couple members, do a little like running the analysis and keep on repeating it for different classes. So let me show you how it works, and then you can like replicate. So the deal is, for example, if we were just looking at the issue of the columns, okay, they have these member numbers, 1 through 9. Okay, so what I need to do is I can go ahead and assign individual members. These are all the different members to different groups that I want to analyze together. Or I can go into the groups and define them and assign the members to them. It's two ways of looking at the same thing. So if, for example, I'm going to put column number 1 in group new. Actually, go ahead. It's easy. I redo it this way. Let me say new this way. Say I have a group number 1. And what I want to do is as follows. For this group number 1, I'm going to go through and put some different members in here. If I want to put 1 in there and only column 1, I can put that. If I put 2 in there, 3 in there, I'm putting different member numbers in there, 4 in there. It'll ultimately figure out and put that little abbreviation, 1 to 4, 1 to 8, 1 to 9. But really what I'm sort of interested in is 1 to 9. That's really all the columns in the browser over here. Okay, next up, we got the whole issue of what the material is that should be analyzed. It's sort of guessing steel, carbon, FY. I'm going to go to steel, ASTM, but again, choose the material that you want and its properties that you want to go through and use. We have the notion of a name for this. Now, calling group number 1 works, but it's not so descriptive. So maybe let's go ahead and call this, I'll call it my columns. Maybe later we'll break it into exterior columns versus interior columns. Okay, we're doing pretty good. Let me save that away. So now I have a group number 1. We're going to go a little bit further though, because what I'd love to do is say, not only do I have to sort of tell it how these things are organized, I actually have to give a little bit of guidance about, okay, well, the steel manual's kind of big. There's a lot of choices out there. Which sections do I even want to consider? Because I don't necessarily want to have a very exotic section relative to what's available in my area. I'd kind of like to have sections that are appropriate. So I can click the Sections button, and you actually get this whole database of really what's valid for our project. So you can look at all these different databases, timber columns. Yeah, I'm going to change it to AISC, to the steel. I'm going to go just to the W sections right now, but again, I could sort of change that to whatever I want it to be. Okay. There's all sorts of different sections there, and if I want to put all of the available W sections in there, I can, all the wide flange sections. I can take some of them out if I want to, but I'm basically saying this is what you have to work with. So go ahead and optimize relative to this. You may only have 5 sizes, at which point you reduce it to that. You sort of give it, really, what is the range of choices? And I'll say okay to that. Okay, so now I got some sections it can choose from. Okay, so with that combination of these members and these choices, okay, we can now go back and kind of do, in the lower part, a specific type of calculation targeted on those. So here's how it works. If I say code group design, I can say, well, I have a group right now called columns. So we'll take a look at that. Next up, I have some options for optimization. And we can go ahead and put some limits on this. We can say, I'd really like to optimize it by the length, or the weight, excuse me. So basically how much the weight of the steel is. I can sort of limit it so that the maximum section height is a certain amount, the minimum height I want you to work with is a certain amount, minimum flange, maximum flange, minimum web. We can sort of give it some boundaries about what's acceptable. So I'll say, oh, nothing bigger than 36 inches, but nothing smaller than, say, 8 inches. I'm just trying to bound kind of the space that it's going to look at a little bit. I'll say, okay, oops, I have to check those on if I want to use those criteria. Say, okay. But I've just basically set up a little, criteria for how you go through and do the optimization, because optimization, we're going to learn, is really kind of tough. There's a lot of things you can optimize and use a little bit of guidance. Okay. Once we've chosen some members, we've chosen some optimization criteria, we are ready to run some calculations. And we do that by saying calculations. And it's going to do a little bit of work. It says, okay, for those columns you gave me, here's how it basically stacks out. If I look at all of those columns together, the code code 1, it's using column 6 as being the bounding case, kind of the one that's really driving the design. It needs to be a 12 by 65. If I go a little bit lower to a 21 by 62, I guess that's by weight. Okay, it's going to be a little overstressed. If I go an 18 by 65, okay, it's a little bit bigger. It's about the same weight, but again, it has. It's interesting. The ratios are funny. It considers that to be the optimum. If I go through and switch to that one, it won't be right. Although I'm wondering what's going on with the ratio, because that looks like a funny number to me. I would expect that to be actually this. No, that's the next size up. That's still overstressed. It's confusing me about what it's telling me right now. Bigger flange, same weight, should be okay. I don't know why the ratio is that way. A little strange. But I can go ahead and kind of go changing through some of these different things. 18 by 65, it's incorrect. I got to figure out why it's failing. It's failing in a different direction.
It should be buckling.
Oh, is that what it's doing?
I guess.
Okay, I would believe that. Okay, so we got those sort of handled, and that's the column. So if we like that, if we think that's actually okay, and this is the size we want to use and apply it on that of these columns, what we can do is say just change all, and that'll apply that, it'll change them all to be 12 by 65. They may only be 12 by 65, I'm not sure. Okay, so next up, let's kind of keep on optimizing this and see if it's any different. For example, let me just close that up. Of all these columns, most of them, there's column 1 on the outside. Let me kind of close this stuff up if we can. Column 2, column 3. Hang on, I'm trying to get this out of the way for you. Trying to figure out what that middle column is. There it is, right there. It's column 5. If I go right there, it's the interior column as opposed to the exterior columns. What I might want to do is kind of go through and be a little bit different about this. I can say that, great, group 1 is really all the exterior columns. And I'll just change the criteria a little bit. I'll say instead of being 1 to 9, it's 1, 2, 3, 4, 6, 7, 8, 9. Okay, and save that. Then I'm going to go through and create a new group. I'm going to say group 2 is exclusively member 5. And it's going to be the interior column. Get the idea? Okay, we'll do the same thing to the beams here in just a second. Let's go ahead and let me rotate that thing around again. If we go through and put the names on the beams, maybe that'll be helpful. Let's go back to the display. And I'll say, let's go ahead and put those bar names on there. Or numbers. Maybe that's easier. I can see that rotating around in here. I got 10, 11. It really has to do with the order in which I drew all this stuff. 10 and 11, it's 12, 13, 14, 15. Running this way. 16, 17, 18, 19, 20, 21. Okay. So, if for example I want to look at these exterior beams, I'll say 16, 17, 18, 19. If I want to look at the interior beams, I'll say 20, 21. Okay, got the idea? So, how do we actually put that into practice? We'll go back over. Let me find my little window. So, a new group. So, what did I thought it was? It was 16, 17, 18, and 19. Oops. Are all going to be the exterior beams. Let me save that away. New group again. I'm going to say that 20 and 21 are the interior beams. You save that away. Look at the idea? Not too awfully bad about what's going on. And it's really just a matter of going through and creating different groups for each of the different cases. And how you group things together in cases, it's really based on, you could go through and itemize each and every case individually and get a specific size for that. But if you want to think about things as being groups of like beams or like elements that have similar functions, it goes through and gives you the driving criteria for that group. Okay, which is actually a pretty smart way to do it most of the time. So great, I got all that. That's looking good. Let me save that away. Let's see if I can find it. There's my calculation window. It's back over there. So what I'm going to do now is, again, I'll do code groups, but this time, as opposed to just doing one, I can really get all the ones in here. So all 4 cases, or all 4 groups of members. Again, choosing how we want to optimize, calculations. So what we'll do now is go through and give us the ability to, for, what was it, the interior column, it's interesting, 12 by 65 over there, 8 by 28 over there. Well, that strikes me as being very odd. Exterior beams 10 by 54, interior beams 12 by 79. That strikes me as being right. This strikes me as odd. I got to think about what's going on. If somehow we're torquing things in some funny way, because that seems like a very funny number. I want to kind of dig into that one some more. Okay, versus these. Okay, but once you go through and you find it, it's what it's recommending as the optimal right now. Again, you don't have to accept that as being the optimal if you say that, I really don't want to go through. There's something very odd about an 8 by 28. I'm not sure what that is. But if you don't want to accept the value in there, like it's suggesting 10 by 54s, you can kind of go ahead and up it up. You can go through and kind of change it. I guess it's using primarily weight, so it's organizing them in that as opposed to the web depth. But if I wanted to go through and make that a little bit bigger, because I just felt that, it would be a little bit nicer if it was a size bigger, I can go through and kind of change that. Well, that's interesting. No, it is. Okay, this is interesting because no, it is not right. It's funny. Let me change something different. It's optimizing by weight, and I can tell that it's actually giving me the wrong result because, it's not okay. What's happening here is you can sort of see that the ratio is not right here. So just optimizing by weight isn't doing the right thing for me. I should go ahead. Neither of those work. This one I could go up to a 14 by 30. Okay, but somehow in my optimization criteria, I'm choosing something wrong because it's I'm optimizing weight as opposed to functionality. Let me close that up. Back over here, let me take weight out. Sure. And now, let's see if that gives me any better results. Now that actually looks a little bit better for what I was hoping. It's interesting here. Okay, the functionality looks right. Yeah, this is stacking the way I would expect it to stack, taking weight out. In terms of, what's going on over here? That one being a little same flan or same depth, but heavier weight per foot. same depth but heavier, same depth but heavier, same depth but lower. Okay, this feels a little bit better in terms of the result I'm getting. So in any case, the idea is you can run through this stuff, go through and say change all, and as you do that, you're basically putting all those changes back into the model, so you can go through and use it. Okay, let's go ahead and close that on up. Got my calculations kind of hanging over here. That's looking good. Okay, so we can keep on doing that even for those intermediate beams and those braces and sizing those all up. So finally, if I just go 22 through, I believe it is, I think it's 41 is the last one over there. So in new case again, I'll say 22 to 41. I'll call those my, my cross beams. Save that away. Again, can put that in the analysis. Add it in there. And things should be looking pretty good in here. Okay, again, I'll change all to sort of get those sizes. So what's going on there? Those interior beams, 10 by 54, 27 by 94. That's not surprising to me. And 12 by 30 actually being the smaller cross beams. Now, kind of interesting here. This is looking a little small. We could decide to go and make that one a little bit bigger just to try and get a better connection between the depth on these and the depth on those. Okay, but we will close it on up. Okay, and that's basically how you start to use this thing to go through and make the changes. We close that on up. And we can save that one away, just because I like to save things away so that I have the choice of getting on back here later. So structure optimize 2. We are now ready, if we want to go ahead and take this information back over to Revit, which would be a good thing to do. And I have to kind of remember I have to do this within the Revit application. If I come back over to Robot Structural and I say the link, now that's over there. Use a RTD file. This is send the model. This is update the model and results. That's when we're sending things that way. I actually want to sort of pull back this way in terms of what's going on here. So let me see if this will, not sending, no. Is it updating the model? Let me try this. Select reader, modified elements. Project, ignore it. Okay, let's try it. This looks like it is going to, I can only update the parts that are currently selected, or I can update everything. So whether they're selected in Robot or not, I can select the modified elements just so I can sort of see what changed in Revit. And I can, if we've done any work with the connections, we can do that. We'll see how this works. So it's going through, it's pulling from Robot Structural, reading all the values from that application. Hopefully doing okay. And we should get a new framing plan. Doing its work. I'll say no. Okay. Those things, the things that are highlighted right now, are all the things that it says Robot Structural Change. Let's see if we can sort of figure it out. So even in here, it's looking like there's some big old beam in there, and that looks like it's the 27 by 94. It looks like these are now the 14 by 68s versus that one in the center, which is the 18 by 35. And all those little guys are still the 12 by 30s. Okay, so it looks like it pulled the values across. So why did we do all this? It was really, now that we have that structure figured out, we can, in our BIM model, have accurate sizes so that we start placing ducts and pipes and everything that we want around them. And that's really the intention behind this whole workflow, is that you can have a BIM model and a structural model working together and have that bi-directionality in terms of what's going on. If I go through and change something in Revit, we can take it back to Robot. If you change some more in Robot, you can take it back to Revit. And I'm using Robot as my example here because it's what I have loaded on my machine, but if you want to do that with E-tabs, the same sort of functionality works there. So I did it to a steel frame structure. If you want to try it with a concrete frame structure, it should work essentially the same. It's the same basic algorithm, different types of code being used, but it should take you both ways. Okay, so let's just pause and reflect there. How's that kind of feeling in terms of, as a capability, it's kind of cool. In terms of actually getting it done, robot structure is its own separate beast. Learning a structural analysis package is a little bit intimidating in terms of everything it can do. It really is an incredible Swiss Army knife. And in terms of what we're doing in this class, I'd say, don't panic if that is feeling a little out there relative to what you're comfortable. If you've never really had a lot of structural analysis background, appreciate it, understand when you're working with structural engineers, this is kind of the process and what's happening, alongside your architectural work. But don't worry if it's not completely making sense in terms of all the precise calculations. If you're a structural engineer, push it further in terms of really understanding, how different things that we do within Revit get used in the analysis tool. So, if that just basic framing is looking very basic, think about, if you have shear panels or shear cores or something like that, how you can analyze both the steel and the concrete as some sort of composite structure and play around with it on that side. Because the capability is there. There's a lot about robot structural I don't understand because it really is kind of an incredibly powerful thing. But for what you want to do relative to your project is, it's again, not worry about going through and analyzing the entire structure in great detail, but at least for some little piece of it, chill off some little piece of some floor that is relatively regularly framed. See if we can at least, get some sort of an idea of really, am I way off mark or are the members about the right size? Yeah.
What do you recommend we use if we have wood framing?
With wood framing, I would take it again to robot structural because it in the same sense has.
You said, like steel and concrete. Is that
Actually. But it'll work for the wood too in terms of it has a whole, in the same sense that we have the steel design, it has wood design. Okay, so in terms of some of that. So So go ahead and play with it. I think we're all going to learn a little bit with our different framing systems. Lonnie and Raj and I, we're all going to learn a little bit in terms of trying to get through that. But that's okay. I think the spirit of the whole class is really, we may not become masters of how to use the tools, but we at least are exposed to them enough to start thinking about how they will fit in. And everyone's structure is so incredibly unique and different that I guess mastery is not the point as much as kind of starting down the path of experimenting. So see how far you can push that. Any general questions about that, or you get a sense of really what it can be doing? The big thing is this is it can be doing it, and then you can have that sort of bi-directional functionality. So sort of making sense? Okay, beauty.